All right, so this one. The speed of a hockey puck decreases from 45 meters per second to 44.6, so it's not going down that much, and coasting 16 meters across the ice. What's the coefficient of friction between the puck and the ice? Now, we've never had to do a problem when we solve for the coefficient of friction, but what that means is we're going to be combining energy and what we know about force problems. So if I were to draw a force problem for the puck in this example, I'm going to have a puck, and the only force acting on the puck, meaning the only force that's causing the puck to slow down, is the friction. So in addition to friction, I know I have a formula that friction is mu Fn. So somehow I now have to also see how can I replace Fn? Well, we also know vertically the force down, which is the weight of the object, has to equal the normal force. So we have the weight and we have the normal force. So what I can get from that is I can get an expression for friction in terms of the coefficient of friction. So since that's the unknown, I somehow have to incorporate that into my problem. So I know W also equals mg. So if Fn equals W and W equals mg, then I can say that Fn equals mg. And I know that friction equals mu Fn. So if friction equals mu Fn, then friction also equals mu mg. The one thing is that I know that friction in the problem, when I put it into the conservation of energy formula, I know that that's going to have to be a negative because it's a force that's slowing the object down, not speeding it up. So like I'm not going to put, the direction is here, that's down. I've seen some people, they write G as a negative there, but really the negative should be out here. So my equation, once we realize it's an energy problem, it's KO plus UO plus W equals KF plus UF. So if you're on ice, you're on a level surface. The puck is moving on a level surface. So that means that UO and UF are 0. I've actually done a lab with this to figure the coefficient of friction, where you slide the puck across the ice and we measure how far it goes before it comes to a stop, before it literally stops. And that way I would know that the final kinetic energy is 0 because the final velocity is 0. So I've done that, and we can actually calculate the mu that way. We could either use straight line motion to calculate it, combined with Newton's laws of motion, or we could do it from an energy perspective. But in this one, after 16 meters, it's still moving pretty good. So the ice must be very slippery because we're not losing an awful lot of speed. But this number right here is going to represent, from that number, I'm going to be able to get the original kinetic energy. And from that number, I'm going to be able to get the final kinetic energy. And I have enough information to get the work because I know the work is friction times the distance that it travels. And I have an expression for friction. So the next step is to replace the original kinetic energy with 1/2 mVo squared. Now I'm noticing as I write that the mass was not given in the problem. And a lot of times when you do these, if work is still there, you can't cancel out the mass. But in this problem, I am going to be writing the work in terms of the mass because friction is mu mg. So it will be in every single term. So that's the first term. Now I know the work is a negative work because it's slowing it down. That number is smaller than that number. So I know it's going to be a negative work. So that's going to be minus mu mg, which is the friction, times d. So remember, work is force times distance. So that represents the force. It has to be a negative number because I know it's going to be negative work. And so that's going to equal 1/2 mVf squared. Now, once you're at this point, it's just an algebra problem. Just rearrange the equation to solve for whatever happens to be the unknown, and then get that answer. So mu is the unknown. A couple things I can do here, like I said, the mass is in every one of them, so the mass cancels out, and this fraction, so I'm going to multiply everything by the least common denominator, which is 2. So this is going to be VO squared minus 2 mu g d equals VF squared. And if I rearrange this to solve for mu, I'm going to move this to the other side, or I could move this there and move that over. Doesn't matter which way I do it. So I'm going to move this to the other side, and then I'm going to divide by the negative, the 2, the g, and the d to get mu by itself. So mu is going to equal VF squared minus VO squared over the minus has to be included because what would be left over is just this, which includes the minus, and I'm trying to isolate mu. So minus 2 g and d. So that's minus 2 g and d. And remember that the mu doesn't have a, I mean, it shouldn't be negative. It's going to just be a number. So solving for mu, it's going to be VF squared minus VO squared over minus 2 GD. So VF squared is 44.67. They want you to go up to Mr. Steinberg's office, but let me finish this problem before I write this up. So 44.67 meters per second. The other velocity is 45 meters per second. So right there you can see the numerator is going to be a negative number, so that's another reason why we have a negative here, because that number is smaller than that, so the whole top is going to be negative. And we're going to divide that by 9.8 meters per second squared, and the D is 16 meters. So if you put that in your calculator, you're going to get, what was the number that I gave you? 0.094? All right, so 0.094. There are not going to be any units because the numerator is going to be meters squared per second squared, and the bottom is going to be meters squared per second squared. So you get that as your answer. All right, any questions with that?